Okay, so moving on, I'm going to talk about relative velocity, and what we're going to do is there is a formula for relative velocity which we have done before in the previous chapter. This time we're doing it for bodies instead of particles. So I'll review the formula first, then we'll follow it with application of the formula through problems. Okay, so let's say this is a rigid body, and I'll define 2 points on the rigid body, say A and B. Then I'll draw vectors from the origin to A. So this is RA and RB. Okay, then I'll draw a vector from B to A. So this thing here is the vector from B to A. Okay, the first thing here denotes the second subscript is where the vector starts from, and the first subscript is where it ends. So we can write RB. Oh, let me. Okay, it's fine. So RA is equal to RB plus the vector from B to A. So if you differentiate this with respect to time, what you get is VA is VB plus VA with respect to B, where V is going to be dr with respect to dt. Okay, so this is a formula we've seen before, it's nothing new. However, in this case we are doing motion of a body as opposed to a particle. So here's an intuitive way of understanding this formula. Okay, so let's assume that this body is like so, and then what happens is it has a certain angular velocity. It also has a linear velocity, because of which it ends in this position, final position. So this is the final position. Okay. Now, what this formula does is it basically helps us to understand this motion as consisting of two parts: the translation part as well as the rotation part. So what I'm going to do is break down this motion into two parts. So first we'll translate the. So I'm going to redraw this so that it's much easier to visualize it. It's not good. Okay, so redraw this AB. So let's say that it translates. So if you look at the first figure I drew, this one, you can see that the body has also rotated, right? So I'm going to break it down into two parts. One is it will just move about this axis, so it will translate. And then what I'm going to do is I'm going to rotate the body about point A. So rotate about A. So when I rotate it, it will end up in this position. So what this formula tells me is that the motion of B consists of d RB dt. This is the translation of B plus that due to rotation. So that is going to be d R A with respect to B dt. Okay, so this is the first part. This is the translation part, and this is the rotation part. So if you notice here, this is the motion of B with respect to A. So it's actually telling you how the body is rotating. Okay? Yeah.
So do we consider A regarding the rotation being fixed?
Yeah, so it's translating and then rotating. It's fixed about A. So this formula tells you how to relate, evaluate the motion of A as the sum of these two. Now you can also write this as omega AB crossed with R A with respect to B. Okay, omega is the angular speed of AB. So if this line is the same as this line here, then effectively AB has rotated about A. So I'm going to draw this with red. This is theta, and so this thing here is basically theta dot, rate of change of theta.
So this one is still R or omega? This second.
This is R.
Omega, AB, and RAB.
Cross product. So you need to take the vector A, omega AB, take the vector B, A with respect to B, and then take the cross product. So what I'm going to do is I'm going to write a formula for velocity. Velocity of A is velocity of B plus omega AB crossed with R A with respect to B. You could also look at this formula in a different way. If you were told to find velocity of B, it will be velocity of A plus omega AB crossed with RB with respect to A. Okay, both these formulas are valid for the same body. In one case, you're looking at motion, you're rotating about A, the first one. In the second case, you're rotating about B. So depending on what you're interested in, like if you're interested in the motion of A and you're given motion of B, then you would use the first one. If not, then use the second one. Okay, is that clear? Now to briefly mention how exactly to compute the second part. Okay, well, you know how to do it using vectors, right? You can write the ijk and then take the cross product. But there is a sort of a pictorial way in which you can think about this, and that might be easier when you're solving problems. So the key idea is that if this is the vector from A to B, okay, and if this vector is rotating with an angular velocity of omega AB, okay, that's our, so omega AB is what? The vector points in which direction? It comes out of the plane of the tablet, of the paper, right? In order to get omega AB, what you need to do is take your right hand and curl your fingers along the direction I've shown here, and the pointed the thumb gives you the direction of the angular velocity, right? It's the right hand rule.
Wait, which one does your thumb go on?
So take your right hand, curl your fingers along omega AB, okay, this way. Then the thumb gives you the direction of omega AB. So in other words, if this was Ij, Ij is in the plane of the paper, as I've shown it to you, but the vector k would point out which direction? Out of the, right? So k is out of plane. So this omega vector would point out of the plane. It will point in the direction of k. Okay. For that matter, when you do 2D mechanics or 2D dynamics, we'll always see this case where omega points out of the plane of the paper, because we'll conveniently use ij to be in the plane of the paper where we write, and k to point outwards. Okay. And the way you get it is you curl your fingers along the omega vector in the plane, and the thumb gives you the direction of k. So omega AB, the vector, is theta dot. If you like to call theta as the angle which defines the motion, then this will just be theta dot k. Okay? Theta dot is the magnitude of the angular velocity, and k is the direction. It's a unit vector in the k direction. So given that, here's how to intuitively think about omega AB crossed with RB with respect to A. Okay, so this vector, to get this vector, what you need to do is you need to take the cross product of omega with RB with respect to A, which you can do using ijk. But the easier way to think about this is to actually, and this is true for planar motions only, if you take the vector A with P with respect to A, so it's pointing in this direction, right? And you curl it and you move it along the curve, the curled fingers, right? It'll actually give you the direction of omega cross R B with respect to A. What I mean by that is this vector here is going to be in this direction. This is that. Okay, so you don't have to do complicated math for this. You just have to know that when you curl the fingers, so it's something else I need to put here is this is always going to be 90 degrees to this. So this vector omega cross R B with respect to A is right angle to R B with respect to A. Okay, it is right angle, but the key information is that besides the right angle is you need to know the direction. When it's right angle, it could be pointing that way or it could be pointing this way. But the way to get the direction is to look at how omega AB moves. Omega AB moves in the upward direction, so this vector should be in the upward direction. Yeah.
RBA and that vector that you drew are in the same. direction?
So
Are they
this,
supposed to be perpendicular to each other?
yes, this vector is r b with respect to a, this one.
Oh, okay.
And this vector is this vector.
Okay. Okay, I thought the like label to it was another vector.
Oh, you thought this was a vector?
Yeah. Does that make sense? Okay.
Okay, that doesn't look like a vector, an arrow.
No,
Okay.
the arrow
The
right
arrow-
above RAB,
The label RB
that arrow.
/A, the arrow you drew to it was
This one? Oh, this one.
Yeah.
Yeah.
Okay, better?
Yes. Sorry.
No problem.
I don't know if that's too tedious. I was confused.
Again, it will become more clear when we do problems, but there is a very intuitive way to think about this, and we'll use this. So when we solve problems, and I'm going to start solving problems in a bit, but there are two ways to do this. There is what the book likes to call, one is the vector way, vector mechanics way, or the analytical way, in which what you do is essentially you try to write V, B is VA plus omega cross R B with respect to A. Okay, and you basically write vectors for V, omega, and R, and then equate the two sides. So what you have is, for velocity of B, there is an ij component. For the right hand side, it's also a vector, sum of two vectors. It's also going to have an I and j. So you equate the i's on the left side to the i's on the right side. Same for the j's. So this is the vector mechanics, and for this you don't need to know anything about, you don't have to think in terms of pictures, which the other method does. So if you're intuitive, you'd like to see physically what's happening, then I would recommend the scalar mechanics way. Scalar mechanics, or I would call that pictorial, where what you do is you write the same formula, but you visualize what that formula really means. So what you do is you find so for each vector, find x component and y component separately. So this is how you might have learned dynamics in, say, high school, where you resolved forces in the x direction and y direction. Right? You resolve force in the x and y directions and equated them. Similarly, this way, what it does, it says find the velocity b in the x direction and equate it to the velocity what you get from the right side by looking at all the x components. Similarly, look at the velocity on the left side in the y direction, and then look at the velocity in the y direction on the right side and equate the two. Okay, so I'll show you the first problem. I'll actually show you how to use both methods, and then you can choose which method you want to really use. Okay, so this is, let's read this question. So if a roller A, okay, roller A is here, moves to the right with constant velocity of 3 meters per second, okay, determine the angular velocity of the link and the velocity of roller B at the instant theta is 30 degrees. So what we'll do is, well, two unknowns in this are omega AB, and the other unknown is so I'm going to stick to this convention where we try to assume the unknowns in the positive direction. So in this case, I'm going to assume that I is to the right and j is upwards. So if I take velocity b in this direction, then it will be in the positive j direction. So there's no hard and fast rule that you need to do that. You could also assume velocity b is in the downward direction, and when you do the math, it will actually come out to be in the negative or positive of whatever it should be. So don't worry about that. You just have to assume it in the right way. So the unknowns are vb and omega ab. So I'm going to show you how to solve this problem using the vector way, vector mechanics, and also the other way. So for vector mechanics, what we do is we use the formula, but we write vector equations for the left and right hand side. So velocity of b is velocity of a plus omega ab crossed with r b with respect to a. Okay, so let's just start writing vector equations for velocity of b, velocity of a, and the rest of those things. So velocity of b. So b has a velocity in the j direction, right? You know the direction of the velocity for b. You don't know the magnitude of the velocity, so I'm going to write this as vb times j. Is that clear? I wrote it like that. You know that b is going to slide up and down, so you kind of know the direction. You don't know the magnitude. Velocity of a is 3 meters per second, and it's in the I direction. So this is going to be 3I. Omega AB is an unknown. Okay. In this figure, I've shown omega AB to be in the counterclockwise direction. So again, if you curl your fingers along omega AB, your thumb points in the k direction. So omega AB, so you know the direction of motion of omega AB, you don't know the magnitude. So I'm going to write this as omega AB, the magnitude, times k, because it points in the k direction, the vector. And finally, r b with respect to a. So r b with respect to a is the vector which is from, always remember, it's from a to b, not b to a. Your answers will get reversed if you assume it the other way. So the vector from a to b will be like this. So I need to write the x and the y component for the vector from a to b. So the vector is basically giving me it's from a to b. It will be the length of the let's call say it's the ladder. It's going to be 1.5 is the length, right? Times the so 1.5. I need to write the x and y component. So this vector makes an angle of 30 degrees with the horizontal or the I component. So it'll be cosine 30 degrees for I, right? But the direction is going to be in the negative. So this arrow here points to the direction of a with respect to b in the x direction. It points in the negative I direction. So this is going to be negative. Okay. Similarly, there will be a y component, but that y component would be in the positive j direction. So it's going to be plus sine 30 degrees j. So is this clear? Okay, what remains now is in this equation, we have basically, I've written down everything I need in this equation, so I can write VB is VBJ equals 3I plus omega A B K crossed with 1.5 negative cosine 30 degrees I plus sine 30 degrees J. So this comes out to be, and you might want to brush up on vector calculus. Okay, what's I cross J? What's J cross K? I cross J is K. I don't know if you use this trick to remember it, but when you have I, when you do I cross J, you'll get K. If you do K cross I, you'll get J. If you go in the other direction from I to K, you'll get negative J, and negative from K cross J will be negative I, and so on. So this is going to be omega AB times 1.5. Cosine 30 is sine 60, so it's minus 0.866. And then I do K cross J. So K cross J will give me, K cross I, this K and this I. Since K cross I is in the counterclockwise direction, it will give me just J. And then sine 30 is 0.5. And then I need to do K cross J. So K cross J, if I want to go from K to J, I need to go in the clockwise direction. So K cross J is minus I because it's clockwise direction. So this is going to be negative I. Okay, this is just one way to do it. If you, I don't know if you, how do you do I cross J? How do you remember to do that? The cross product. Is this how you did it? No?
You just did the matrix.
You do the matrix, okay. You could take the matrix and do the cross multiplication, but I think this is simpler. You don't need to know. It's hard. Okay, whatever you think you're comfortable with. Please review this. This is very important to.
Stick to what you know.
Yeah, just do whatever you think is best for you. Okay, so now I have two unknowns, velocity of B and angular velocity of AB. So I better have two equations. Are there two equations here? Do I have two equations to solve for the two unknowns? No? So there is an I component, there's a J component, so there are two equations. What I could do is I could equate the I component, that's I, and the I component on the left hand side is 0. And then I can equate the J component, and then they should be equal, right? So two equations, two unknowns. Compare I and J. What you get is VB equals minus 1.3 omega AB. And so this is just comparing the J component. And the second equation is 0 equals 3 minus 0.75 omega AB. This is the J and this is the I. So from this, VB equals minus 5.2 and omega AB equals 4. Okay, so note that when the roller A moves to the right, it is expected that the ladder would, or the roller B would move down, and intuitively you know that the velocity of B is going to be downwards. I started assuming that the velocity of B is upwards, but when I did the math, velocity B came out to be negative, which means that the actual assumed direction is opposite of what it actually is. So the velocity of B is actually downwards. So that makes sense. Omega AB is in the clockwise direction. So when this thing is going downwards, omega AB, or the ladder, is actually turning in the clockwise direction, right? If A is moving to the right and B is moving down, then obviously this thing is going to turn this way, which means it's in the counterclockwise direction, which means omega AB is positive, or in the direction I assumed it to be. It all makes sense. Is that clear? Now you could do this using the other method, the scalar method, and when you do problems, as I said, you could use either of the two methods. Okay, for the scalar method, what we'll do is we'll look at the x component on both sides, equate the two. Look at the y component, both sides, equate the two. Just similar to how you do when you, perhaps in high school when you did forces in the x direction, forces in the y direction, equated them. It's very similar to that. So, velocity of b in the y direction. So we equate things in the y direction, so I'll denote it by this arrow. So velocity of b in the y direction is, well, you know what, let me write it in a different way. So this equation I'm going to write this equation in a slightly different way. So velocity of b is what? In the y direction. So I'm going to write this as v b y equals velocity of a is this. It's in the x direction. So I'm going to write this as vax. If you like, you can write it like this because that denotes the direction of velocity of b. This is velocity of x plus omega a b r b with respect to a, and this thing is going to be in what direction? So as I said, we don't have cross. This is going to be a scalar equation. Okay, this doesn't have any ij. If you want ij, then you want to use the vector mechanics way. The scalar equation, and the directions are the key things. So this actually has more information than it has. Looks like it's just scalars, but by putting in arrows, I'm able to convey that it is actually a vector equation. There's something in the x and something in the y. So I need to find the value, the direction of omega ab cross rb with respect to a, and this is where that pictorial representation I showed earlier will help me. So r p with respect to a is the vector in this direction. Sorry, it's going to be exactly opposite direction. So I'm basically drawing this ladder. This is A, this is B. Okay? So the vector from A to B is R B with respect to A, and omega AB is this way. Again, it's that way because this is counterclockwise, so I've assumed it to mean the K direction, right? So it should be counterclockwise. So what you need to do is, yeah, question.
So up in the top picture, we drew the omega difference. We still call it AB. It's the same thing, like because we're calling the vector RBA, and so in that direction to make a difference. But we're
RAB and RBA have nothing to do with omega AB. Omega AB is independent of RBA or AB. So I drew the vector RB with respect to A, I drew omega AB, and as I said, what you need to do is, you need to turn the vector to get this term. You need to curl your fingers along, you need to take the vector AB and turn it in the direction of omega. So this is the vector, this is in the direction of RB with respect to A, and when I curl it this way, this vector points that way. So this thing here is omega AB RB with respect to A, and it's 90 degrees. So it's always going to be right angle to the vector B with respect to A. If you want a direction, however, you need to look at omega AB. Okay, you need to curl your fingers along omega AB to get the direction of omega AB crossed with RB with respect to A. So this vector is in this direction, and so in this figure it's going to be in this direction. So that direction this is 90. I'm going to draw the horizontal here. So this is 30, so this is 30, so this is 60 degrees. It's 60 because this thing here this angle is going to be the same as this angle, but this whole sum should be equal to 180, and so this angle has to be 60 degrees, and so this vector here is at 60 degrees. Okay, so this is a scalar equation now, in the sense that I've written down the equation and indicated the direction separately, and now what I do is the same thing which you guys have done for, say, problems in perhaps in high school physics, where you took the x component, equated them, y component, equated them. So VBY equals omega A B R B with respect to A. Again, this is a scalar. What I need to do is I need to take the cosine of, so this is this is the y component, so I need to take the sine of 60 degrees. Right? This is giving me the y component. And since the y component for this is pointing in the negative direction, this is going to be negative. Okay. So what I did was I took the y component, this is right here, it's upwards. In this is only in the x direction, so there's no y component. And finally this part here, the second part on the right hand side has two components, x and y. I took the y component, put it here. It's negative direction, so there's a negative sign. Similarly, yax equals, I need to look at the left hand side first, that's 0. There's no x component on the left hand side. Then there's vax on the right, positive I, and then there's going to be omega AB times RB with respect to A in this direction, right? So it's along the negative I direction. So this is going to be negative omega AB RB with respect to A cosine of 60 degrees. So omega AB is an unknown, VBY is an unknown, VAX is given to me. This is 1.5. I know sine 60, this is 1.5. I know what is cosine 60, I don't know this. So two equations, two unknowns. And you can solve for the unknowns. Okay, so it's up to you what you want to use, which method you want to use. Is that clear?
Would you recommend vector over scalar?
It